Before we finish the discussion on spray atomization, let me give you an example to show the detailed spray field or two-phase flow field for a given spray nozzle. And those data actually taken from the Dr. Hong, graduate from the IAA, and I took those data from his PhD thesis. Dr. Hong now is already graduate and working on in a Zhongshan Science Technology Institute, and his advisor is Dr. Wang, already retired. And I think this thesis is very nice for us to study the detailed flow field for given a spray atomizer. He did an elegant experiment, and you can see those kinds of flow velocity and also droplet size distributions. And you can understand the whole spray characteristic for given atomizer. In his PhD thesis, actually, it did a lot of measurements on sprays, and the typical spray nozzle basically show here. Now we are in the page, let me see, it's a 3.14a. A means we add those material additionally for your references. Okay, and this is basically is a so-called simplex nozzle, as I explained earlier. And for the simplex nozzle, the diagram show you the fuel, or in this experiment, basically is air, the water, and the liquid will go through the several channel tangential into the swirling chamber. And you can see the cross section of the nozzle show you the liquid will flow into the conic shape tip, and they will have this kinds of swirling motion, and this swirling motion will push your liquid out of the opening of the injectors, and they already have since there is the swirling motion, then they have a certain amount of centrifugal force, and this centrifugal force will push your spray angle be open, and you will produce the spray cone. And this is the basic structures coming from the design on a simplex nozzle used for gas turbine. Okay, now let's look at the flow structure. The geometry for your flow field basically is like this. The top one basically tell you the injector, there is the tip. Okay, the origin or your coordinates for measurement actually located at the tip of your injector, and there is the two linear lines represent the boundary of your spray. Okay, and here they tell you there's a plotted straight line, tell you there's a pair or recirculation zone very close to the injector port. Okay, and along radial distance we use the r to represent it, and the actual distance will be represented by z, and we will have a radial velocity denoted by v, and the actual velocity denoted by u, and basically all the spray coming from the top and move to the downstream. Okay, now this is a geometry we may have for our measurement domain. Now we start to learn the spray catalyst. For example, they do the flow visualization. For the case one, if you have a higher velocity, the injection velocity is high, and then in the inside of the injectors, they will produce a strong swirling. Then you can see there is a large spray angle be open, okay, near the opening of the injector. And actually, since they try to enlarge the image, actually the distance for the liquid sheet is very short. Okay, and you can see there is the region for the liquid sheet, and later on you will find some ligaments, And in the downstream side, basically you can see a lot of tiny droplets exist. If you decrease the swirling velocity, then you will see the spread angle become smaller, and you have a longer, you will have a large area for the liquid sheet, and atomization become less effective in the downstream sites. Even you can decrease the the velocity smaller, then you will find out there is almost no atomization occurs for these situations. Now we try to look at the measurements on the detailed flow structures. The first one here, they did an experiment that actually they tried to find out the interactions between the gas phase and also liquid phase. What is the meaning of gas phase? Gas phase means that there is some air coming from the outside, right? Then you need to examine the velocity of the air, since they will tell you some mixing conditions for the air with the vapor. And the other one, you need to know the droplet size and the liquid velocity. Therefore, in their experiment, they try to provide certain seeding particle. In this experiment, they use the kerosene. The kerosene, you heat it up, the kerosene will produce some carbon, okay, some kinds of soot, and those soot has a very small diameter. They can follow the flow of the gas, the gas flow. That means that when you have those kinds of tiny kerosene droplets, then you can figure out the velocity of the gas flow. Okay. Then they use the data coming from the measurement on the kerosene droplets and to identify the behavior for the gas phase. But for the droplet, for water, they use, since water is a very good sealing particle, right? But the size of the particle, the water droplet depends on the spray characteristics. Near the tip of your nozzle, you will have a large droplet size for the water, but in the downstream, maybe the droplet size will become smaller and smaller. But anyway, in the process of atomization, actually water droplet itself can play as the sealing particle. Then you can have some data coming from this the motion of your water droplet. Okay, which means now in the experiment there is a two set of data. One set coming from the kerosene tiny sealing particle. The other one is coming from the water droplet itself. And you can identify the flow motion on gas phase and the liquid phase and do the comparison. Okay. The first one, they tell you when you have a large momentum of the liquid jet coming out, it's very similar to the gaseous jet. You will have a certain so-called entrainment coming from the outside, that there's some air entrain into the interior of your jet, of your spray jet. Okay. Now they just want to show you they can do the measurement on gas entrainment at the nozzle exit plane. Okay, at the nozzle exit plane, this is the plot. The lower one represents the radial velocity distribution. The upper one represents the actual velocity distribution along the radial coordinates, starting from the center point. 0 means the center of your jet. Okay, and when you increase the r radial distance, then they will move to the surrounding region. Okay, you can see here when we look at the actual velocity first, you can see there is the highest actual velocity around maybe r divided by d equal to this will be the 10, something somewhere here, but they will reduce continuously to the outer surrounding environment. And this tells you actually the actual momentum is reduced to along the radial distance. And here there is a reduction on the actual velocity. Later on, I will show there is a recirculation zone, right? From the beginning, I already mentioned this is the flow structure you may have for the simplex nozzle, since they have some swirling motion. The circumferential force will produce some force to expand the spray, and also they will have some air coming in and traveling in, and those kinds of swirling motion will produce a pair of recirculation zone. And here they will tell you some reductions or the decrease of actual velocity occur here. Okay, but later on you can see those kinds of velocity of the droplets where they will show the different directions under in the recirculation zone. And here the lower part tell you the distribution for radial velocity. You can see there is a minus sign. Minus sign means the flow coming from the outer region to and point to the center axis. Okay, then they just give you a reverse directions. Okay, in the very far surroundings, the environment, actually they do not have any influence coming from the flow. Then the velocity, the radial velocity is almost to zero. But when you measure closer to the center axis, the radial velocity becomes stronger, and become very large when they closer to the spray cone. That means that you have a very strong axial momentum of the spray, and this axial momentum will push all the liquid, and also near the gas near in the vicinity of the spray tip regions, they will move forward to the downstream sites. Okay, in this case, the air basically is entrained into your spray cone. Okay, when you closer to the almost the radial distance ratio around 10, they will give you the very large radial velocity up to the 1.6 meter per second. Okay, and this behavior simply to tell you there is an entrainment near the exit plane of your nozzle. Okay, now let me shift to the other slides, because I need to make it has some turn. Let me change it a little bit. I'm sorry, okay. I stop this and I open, yeah, another, okay, now, yes, this is good. Now we try to look at the actual velocity distribution and the radial velocity distributions in different cross sections for the spray from the vicinity region, from the vicinity near the spray nozzle up to the very far downstream. You can see for these two figures, two sets of figures, we have a measuring point from the based on the ratio of your actual distance normalized by your droplet diameter. I'm sorry, the D is the size of your nozzle. Okay, from the 10 up to the 50. Okay, from 10 up to the 50. Basically, from the top figure represent the region near closer to the tip of your injector, and move to the lower figures represent the cross sections in the downstream region. Okay, and the left hand side represent the actual velocity distribution. Right hand side represent the radial velocity distributions. Additionally, in both figures, they tell you there is the two sets of measurement, right? The open cycle represent the measurement on water droplets. Okay, and the solid circle represent the measurement coming from the kerosene particles, representing the gas phase velocity. Okay, and there's a comparison. Let's look at the behavior on the spray. That means the water droplets. The motion of your droplet, you can see near the nozzle tip. You can see initially they have a very high velocity, is around maybe 15. Let me see, this is 16 meter per second, and in certain place, actually, in this case, you understand the simplex nozzle has a swirling motion. The influence coming from the circulation force will open your spray angle, and you may not have too much water droplet exist in the center region. Actually, they produce a so-called hollow cone spray. Hollow cone spray means that the droplets will more concentrate along the spray boundary, and in the interior of the spray region, they do not have too much droplet exist, and all the spray momentum inside of the spray cone has less intensity. Okay. In this sense, you can see initially there is the smaller actual velocity region. Okay, but when you move to the when you increase the radial distance, you will find out they will reach to the maximum value at this point. Actually, you can imagine this as very closer to the boundary of your spray cone, and later on they will decrease. Okay, and those kinds of distribution continuously expand along the actual direction. So you can see the actual velocity, the maximum actual velocity basically is reduced, but they will extend to the larger radial distance. Actually, later on you will see the thickness of your spray cone become thicker in the downstream sides. Okay, and additionally, you can see in the center regions there is a small region has a negative axial velocity, right? What is the meaning of negative axial velocity? Even the velocity is very small, but they tell you there is the recirculation. When you have a recirculation, means that the axial flow will reverse to have a negative direction, point to the injectors. But those kinds of recirculation will disappear as you move to the downstream side, which means that the length of the recirculation zone basically is small, and they are very closer to the exit plane of the injector. Okay, and additionally, you can see near the center region, actually those flow velocity for both gas and liquid are small, and they are almost the same. Okay, okay, you can see in the interior of spray cone, uh, the open circle almost coincide with the solid circle. Okay, but there is a big difference along the spreadsheet. Okay, under the spray boundary, actually those kinds of the water droplet has a bigger size compared with gas phase, and they have a strong actual momentum. Therefore, the actual velocity is much higher than the gas velocities. Okay, and this behavior extends continuous to the further radial distance. Okay. And we go to the right hand side. You can see the radial velocity profile. Similarly, radial velocity profile tell you there is a recirculation zone here, right? And this recirculation zone will disappear completely at the section of the Z divided by D is 20. Okay, around here. And the similar way, you can see there is the highest radial velocities very closer to the boundary of your spray jet. Okay, spray sheet. And there is some near the spray nozzle. There is some entrainment. You can see this is a negative value, right? Represent the entrainment, but those kinds of entrainment will be reduced in around the downstream regions, and the extension of the high temperature, high velocity regions to the radial directions is very similar, and can be compared with those kinds of characteristics in the left figures. They tell you the extension of the spray region from the injector port to the further downstream. And those kinds of velocity distribution just give you the idea to think about all the radial and the axial velocity distribution along the axial directions, and it is more easier to understand the velocity variation by velocity vector and the plot. The velocity vector distribution for different size of the droplets, and also for the gasoline droplets or gasoline particle. Okay. The first one, figure 7, represents the velocity vector for the gas phase, represented by the kerosene, a tiny particle. Now you can see the motion of the particle actually coming from the outer region, but when they approach it to the spray region, there will be accelerate. This acceleration basically coming from the entrainment, the pressure difference, and they will they will drive all the gas flows move into interior of the spray, and they move into the interior of the spray. They will be accelerate and follow the motion of the liquid drop. Then you can see there is a recirculation zone here, very close to the tip of the injector. Okay. But in the downstream side, they just follow the liquid droplet, the spray momentum, move along the central line and to the downstream side. And this is a very nice pictures from the experiment data, and to let you know the motion of the gas flows in a spray flow field. Okay. Now we look at the motion of the droplets. Okay, the first one, we focus on the droplet size as a 5 micron. It's a tiny one. It's a small water droplet, and they represent the small particle moving in the flow field, in the spray field. Actually, the motion, basically, you can see they follow here. There is a more there is a higher droplet velocity, right? Droplet velocity, because they just coming from the injectors, and they have a strong axial momentum, and they were more concentrated in a small region. Actually, this is tell you the region of your spray, okay? And those kinds of region will be extend further to the downstream. And here, easily you can see there is some recirculation zone. Tell you the droplet has the velocity vectors. They will change their directions in these recirculation regions. Okay, and here we go to the next plot for the 10 micron. Actually, the motion, the velocity vector distribution is almost the same compared with the 5 microns. If you increase further to the 20, 30, you can find out the velocity vector measure and the measurement data for velocity vector become this. For example, for the 30 micron, actually you do not have some velocity vectors exist in the center regions of the spray, represented for example, for 30 micron, 50 microns, 80 micron. Those droplets are very large, and they do not have a chance to be pushed into the interior region. The interior region of the spray, basically, they do have a small velocity, and they do not have a strong momentum. Actually, all the spray momentum were concentrated on the region, a small region of your spray sheet. Basically, you can see there is a spray sheet extension. If you look at the 80 micron, okay, you can see near the tip of your nozzle, the region of your spray cone, actually, the thickness is very small, but the thickness of your spray cone will extend along the axial directions, and they will spread to a large region. Okay, and in this region, all the velocity vectors show you has a large intensity of your velocity speed or your speed, right? And in near the near the vicinity of injector, they have a larger speeds, and those speeds will continuously reduce because there is some mixing in the downstream sites. But anyway, from the 50, 30 micron, 50 micron, and 80 micron tell you the thickness of your spray zone initially is thin, and you in this region you have a larger dropping velocity. But later on, the thickness of your spray cone, the spray teeth will be extended, and you will have more air entrainment. Therefore, the dropping velocity will become smaller, and but the spray region will extend further in the downstream sites. And we go back to the previous figures. I think this is the last slides for this set of experiment data. Here, they try to give you the other spray characteristics. You remember we emphasize if you want to quantize the spray characteristics, you need to consider several factors, right? And the droplet size is the most important one. Here, they do the measurement for the droplet size based on the spray characteristic. We already explained this is a D32, D32. That means a saw mean diameter. The saw mean diameter basically represents the total volume of your spray you have divided by the total surface of the spray you have. Then they will give you the typical droplet diameter to represent the burning of your spray. Actually, they will get involved with the total heat release rate compared with the gasification strength. Total heat release will based on the volume of the droplet you have. But for the gasification will depend on the surface you have. If you have a large surface of your liquid, then you will have a strong gasifications. And we bring these two factors together to give you a very nice typical identity for spray. We use the sodium diameter. Okay. Now, the size of solid diameter distribution, you can see along the radial distance for different cross section along the actual coordinate. You figure out, as I explained earlier, when you have a near a closer regions to the injectors, actually the thickness of your spray cone actually is smaller, and the spray distribution actually is more dense, and they have a strong axial momentum, and the droplet size should be large. Okay, here this is the distribution. You can see for Z divided by D equal to 5 is a spherical symbol, represents the thickness of your spray region is thin. Okay, and they have a larger droplet size. Additionally, you can see there is the volume flux show you there is the more dense. They show you that this is a dense spray region. What is the meaning of volume flux? They tell you in this region how much droplets you may have. Okay, and then they calculate the total volume. Okay, total volume in these small regions. And you can see in this region for the region at J divided by D equal to 5, then you can find out they have a larger droplet size, and also you have a more droplets in this region. But when you extend further to the downstream side, as you increase the actual distance ratio from 7 to 20, you can see the droplet size, they do not change too much actually at the maximum point, but they extend to a large region. Actually, they tell you those kinds of extension of your solid diameter distributions, basically they follow with the extension of your thickness of your spray sheet, okay, spray cone, the spray boundary. And then you can see later on, you can see at the end of the measurement, J divided by D equal to 20 times droplet the injector diameters. You can see all the size distribution extend to a very large area that they can cover in a large region in the downstream of the spray. And in this region, you can find out for the solid angle, solid triangle symbols that tell you the number density becomes smaller because in the experiment some water will be have some gasification. Then all the size or the smaller size will be gasified, and the numbers even they will extend to a large region, but total boiling flux reduced and you extend it to a large region. Okay, you can imagine the spray behavior from the tip of your injector to the downstream by following the droplet size and the boiling flux. You can see originally closer to the exit plane of injector, there is a thin spray sheet. Okay, in that regions you will have a large number of droplets and with higher velocities. But later on, when you move to the downstream sides, those kinds of distribution will extend. That means the spray regions along the sheet they will extend further in the downstream side, and those kinds of extension will give you the more mixing with the outer air. And at that time, you will find out in that region, in the downstream region, the spray become more dilute compared with the dense conditions near the injector point. Okay. I think this finished the discussions on the spray field. You may have for given spray injector. This is a typical example to let you know. And but this is not just almost complete the same for different kinds of spray field, and you may have a different spray flow field. For example, you use the high pressure nozzle and you produce a hook cone sprays, then all the distribution will be different. But this is just give you the practice to know the interaction between the liquid droplets and also the gas phase, and to see the variation of your droplet size and the spray behavior, including the axial and the radial velocities.